So this is an example of a logic gate. This is the AND logic gate because we want both A and B to be things. And we have a diagram. And so you can imagine, there's electricity flowing through a wire, A, and then the gate has to decide, will there be electricity flowing through the output or not? Okay, so in our first scenario, there is no electricity which we can going through A, we can give that a 0, or no electricity flowing through B, and we can say the same thing. So input A is 0, input B is 0, and in this situation, the output, that's an O in the black, is also 0. So that's our first row. Let's have a look at another situation. What if we had electricity flowing through A? We could go that a 1, and there's still nothing in B. This still actually means we got nothing in the output. So we can have 1 in A, 0 in B, and still 0 in the output. And we can just look at this again. There's nothing special about A or B. So this is just a mirror image of our previous situation. And so we get the same thing. So instead of being 1, 0, it's going to be 0, 1, still gives us no output. And finally, for AND, we can say, well, if we've got A and B both being 1, then we do get something in the output, and we get a 1, so we get 1, 1, 1. Okay, so now we've got an OR gate, which looks slightly different because it has this curvy back here. So that actually is important. Now, A and B, that's the same as we had before, but we've also got this A or B being acceptable. So our first input of 0, 0, and 0, that's the same as before. We get nothing in, nothing out. But if we do A, 1, and B, 0, no electricity, we do get electricity out, which is this situation here. We got the 1, we got the 0, we got the 1. And again, it's just by symmetry. If we have a 1 and a 0, we get a 1 flowing out, which is this situation here. And we already had from before, if you have a electricity, you get electricity out. That's 1, 1, 1. That's this guy here. So that's an OR gate. So it's similar to what we had before, but now we've got A or B is okay, and we have that curly shape. Okay, so we're doing a NAND gate this time, and that just stands for not and. So it's the opposite of and we demonstrate this by having this little circle thing on the end of an AND gate. So it looks exactly the same picture, but now it's got this little circle at the end to say not. Okay, so if we were to look at the situation of the AND gate, which we did before, we saw this over here, and we can now say, well, hang on a minute. So wherever we had a 0, we have a 1. So we had a 0, we have a 1 again, and 0, we're going to have a 1 again, and then when we had a 1, we have a 0. And that's just the opposite output from an AND gate. Okay, again, we can see that this is an OR gate. We can see that little curvy back, which is different. And we can also say it's got a NOT symbol on there because this is NOR for not OR. So if we saw the OR was 0, 1, 1, 1, the output here should be 1, 0, 0, 0. And that's quite a strange thing actually to think about, because you're saying no electricity coming in and electricity coming out. Which you'll find with the dominoes we can't do, because that's like with the dominoes, 1 is knocking them down and 0 of them staying up. But if they're staying up, how do they knock things down? And now we come to the XOR gate, and we can see it's got this interesting, it's got the curve of the OR, but it's got a double line there. All right, so that double line, which I've just fuzzed over, means we only want, in this situation, A or B, but not A or B. So just by symmetry, this one is always the same as this one. In the outputs, they're always like a pair, so they have a 1. But this time, if we've got electricity coming in, which is a 1, and electricity which coming in, which is a 1, we don't get electricity out, which is a 0. So we actually want a 0 in this case. So we get 0, 1, 1, 0 as our output. Okay, so we can see we've got a XNOR gate here, XNOR, which is for the X for exclusive, N for not, and the OR. So we can see the OR for the curve, the exclusive because you've got the double curve, and here's the not part. So you can see it's all just built up on the picture as well as it is in the naming. So if you think about that, what we want is we're saying not A and not B. So if you just have A coming in, we've got A input, B nothing. So that's like this, A 1, B 0. The output is going to be 0. And by symmetry again, if you had B coming in and nothing in A, you would get nothing coming out, nothing. And if you have something coming in A, something coming in B, you do get something coming out the output. So you get 1, 1, 1, 1, 0. So it's an exclusive not OR gate, XNOR.